So we're lucky to have Taichi Uemura from the University of Amsterdam with us today, and he'll be talking about the universal exponentiable arrow. So you can start when you're ready, Taichi.
Okay. Thank you very much, and thank you for inviting me to this seminar. Right. So yeah. So today basically I construct a universal exponentiable arrow, by which I mean a pair of category with finite limits G and an exponential arrow D, which is initial among such things, in the sense that given any other such a pair of a category with finite limits and an exponential arrow, then there exists a unique structure preserving functor from G to C. And by unique, I mean unique up to isomorphism. But I do not only prove the existence of such an exponential arrow, but also give a concrete construction of the universal exponential arrow. Precisely, this category with finite limit G is characterized by this equivalence. This category of left exact functors from G to Z is equivalent to the category of generalized algebraic theories. All right, so this is my main result. Namely, the category of generalized algebraic theories can be presented by certain universal exponential arrow. Yeah, so this I have a preprint on archive, and I gave a syntactic proof. But today I give some different proof using a kind of semantic counterparts called contextual categories. Okay. So I first explain some background and kind of motivations. So in general, I am interested in categories of theories. So there are some categories whose objects are considered to be theories. For example, meet-semi lattices, algebraic counterparts of propositional theories with top element and conjunction. And also categories with finite products, algebraic counterparts of many sorted algebraic theories. And also for finite limits, it corresponds to essential algebraic theories. And yeah, so the main topic of this talk, contextual categories, are algebraic counterparts of generalized algebraic theories. And I'm also interested in the higher dimensional things like infinity categories with finite limits, which has been proved that they are equivalent to dependent type theory with intensional identity types. And yeah, one of the ultimate goals of homotopy type theory is to define a good notion of elementary infinity toposes and give a connection to univariant type theories. So yeah, so there are many notions of theories, and they form certain categories or even infinity categories. Then I ask, is there any property do these categories of theories have in common? Basically, this is one of my motivations. Okay. So an immediate fact is that these categories are essentially algebraic because they are algebras. So, and being essentially algebraic is equivalent to the locally finitely representable, or it is also called compactly generated in the context of infinite category theory. Anyway, then by the Gabriel majority, if given a category of theories which are locally finitely presentable, then we can find the category finite limits, which I'll denote by Tx, such that X is recovered as the category of left exact functors from Tx to set. So in that sense, instead of asking the properties of X itself, we can also ask properties of this category's finite limits. And my claim, it is a little informal, but my claim is that given a category of theories, then we can characterize this category's finite limits as a free category generated by generated under finite limits and with a special exponential arrow, maybe some other maybe with some other structures. So in this case, we will see some concrete examples of categories of theories and find a special exponential arrow. Okay, and as I said, the goal of this talk was to find a universal exponential arrow in Tx in the case of X is a category of contextual categories. But actually, the structure of a contextual category is a little complicated. So as a warm-up, we begin with a category of meta-semi-lattices, because meta-semi-lattices are much simpler than contextual categories. So I think it is nice to start with. And so anyway, so when X is a category of meta-semi-lattices, I will show that the corresponding category is finite limits is generated under exponential monomorphism whose associated internal period is an internal meta-semi-lattice. It's a little long, but and then next we will see the case when X is a category of contextual categories. In that case, Tx is a free category generated under finite limits and an exponential arrow. Okay. So this is the contents of my talk. So I first give a quick review on exponential arrows and stellar categories. And then I explain a kind of general strategy for finding an exponential arrow and proving the universality of the exponential arrow. And then apply this such a proof scheme to concrete examples of meta-semi-lattices and contextual categories. Okay. So we first recall the definition of exponential arrow. So let's see be a category with finite limits. Then arrow in this category is exponential if the pullback functor along this arrow has a right adjoint. The right adjoint is sometimes called push forward or maybe dependent product. But so intuitively, this right adjoint constructs a kind of function space-like object. Okay. So there are some other equivalent conditions for exponentiability, which I use in this talk. So first of all, use exponential if and only if the push out functor along the push-out functor along the image of the control variant unit embedding has a left adjoint. This is understood as a consequence of the Gabriel modularity. So observing that under the Gabriel modularity, the slice of a finitely complete category is sent to the co-slice of the corresponding locally finitely presentable category. So, and the pullback along U has a right adjoint if and only if its corresponding push-out functor has a left adjoint. And then, thanks to the adjoint functor theorem, this push-out functor between locally finitely presentable categories has a left adjoint if and only if it preserves limits. Because push-outs always preserves co-limits, so in particular preserves filtered co-limits, so the adjoint functor theorem applies. Okay, so in this talk, I mainly use this third condition to verify some exponential arrow is exponentiable. Okay. Then, yeah, right. Then category X is essentially algebraic if it is the category of sigma algebras for some essential algebraic theory sigma. Right, and this is it is known that this is equivalent to that X is locally finitely presentable. So we always find the category with finite limits dx. That X is equivalent to the category of left exact functors. And I also use the fact that I also use the concrete description of Tx, namely Tx is a full subcategory spanned by the finitely presentable object and take opposite. Okay, and I also use another description of Tx, namely Tx contains the universal internal sigma algebra, which means that this equivalence holds for any other category with finite limits instead of set. And precisely given any category with finite limits D, there is a notion of internal sigma algebras in D. Then the category of internal sigma algebras in D is equivalent to the left exact functors from Tx to D. So, okay. Okay, so using then I explain somehow to find the universal exponential arrow. Given a category of theories, which I assume locally finitely presentable, so we find a category with finite limits Tx with this equivalence. Then I want to construct an exponential arrow in Tx. So, and proof strategy is as follows. So the objects of X are kind of theories. So there should be a notion of some types or elements or propositions and so on. So there should be some free object generated by a single type sigma. This object is a kind of theory which only contains a constant type symbol. This free object is a kind of theory which only contains a closed type symbol. Okay. And then we can also consider freely adjoining a global element of this type to obtain another free object like this. And together with inclusion. And then the next step is, I think, the most important step. To prove that there is some kind of slice construction which fits into a push-out diagram like this. This means that we can concretely describe the push-out along this inclusion iota. Okay. Then observe that these free objects are finitely representable as you know, their presentations are finite. So, and observing that slice construction preserves limits, then which means that first of all, iota is in the image of the Yoneda embedding, and then the push out along iota preserves limits. So I use the previous characterization of the exponentiability to derive that, to obtain exponential arrow in Tx. Okay. So to summarize, because these three objects are image of the Yoneda embedding, so iota is image of some arrow from Tx. But iota, the push out along iota is given by a slice, which preserves limits. So the adjoint functor theorem implies that this arrow d in T is exponentiable. Okay, so then next we want to prove certain universal property of this exponential arrow. To do that, first of all, we observe that any exponential arrow in any category of finite limits induces an internal sigma algebra in D, where sigma is essential algebraic theory for the category X. Then observe that the internal sigma algebra associated to this exponential arrow D coincides with the universal internal sigma algebra. Recall that Tx contains a universal internal sigma algebra. So we have two sigma algebras, which one is a universal internal sigma algebra, and the other is associated to the exponential arrow D. And we observe that they are isomorphic. And then it is straightforward to see that the given an exponential arrow D in given an exponential arrow U in D, then we have a left exact functor from Tx to D corresponding to the internal sigma algebra associated to U. Then because the universal internal algebra is constructed from the exponential arrow D, then it follows that this corresponding left exact functor commutes with push forward along D. Yeah, actually, we need some reasoning for this third claim, but it's very straightforward. Okay, so this is the outline of so this is a general scheme for finding a universal exponential arrow. Okay, so let us see concrete examples. First, So as a warm-up, we begin with mid-semi lattices. So recall that mid-semi lattices are just poset which has finite limits as a category. Then, of course, the theory of mid-semi lattice is algebraic. So in particular, it is locally finitely presentable. So we get a category with finite limits, which I denote L. That's that this equivalence holds. Now, so following the strategy I've explained, we first construct some free objects, right? So just do it. I mean, this is just a free mid-semi lattice generated by a single object, and then the other free mid-semi lattice is obtained from the first one by adjoining a global section of sigma. But in the context of pre-order, adjoining a global element is nothing but forcing sigma to be greater than top. Then it turns out that this free mid-semi lattice is nothing but trivial mid-semi lattice. Then my first claim is that the canonical morphism between these three mid-semi lattices defines an exponential arrow in the category with finite limits L. Okay, so to do this, we observe slice construction of mid-semi lattices. And in this case, this slice is just a slice of other category. And in terms of the ordering relation, this C over A is a subset of the elements below A. And then we make some commutative square like this, where A star is defined by conjunction with A. Then A star A becomes the top element in the slice, because the top element of slice is A, of course. And then this data fits into this square, namely that is because this mid-semi lattice is freely generated by a single object, so an object A in C corresponds to a morphism. And because this equation corresponds to the existence of this bottom map. Okay. And so I claim that this square, commutative square, is a push out in the category of mid-semi lattices. Maybe it is known, but I don't find precise reference. So unique filler is so given another morphism C to D and another morphism both here, making it outer square commute. Then we have to find a unique filler F prime. And in this case, this F prime is given by the restriction of F. So in general, such a restriction need not to be a morphism of mid-semi lattices, because because the top element of slice is A, but F need not to send A to the top element. But the commutativity of the outer square means that F of A is greater than top. So in this case, this restriction is indeed morphism of mid-semi lattices. And the uniqueness is straightforward. So this proves that the slice of mid-semi lattices, the slice of mid-semi lattice is a push out and observe that these three these three meet similarities are finitely representable, and the slice construction preserves the limits. And then we get some exponential arrow in the category L. Okay. And also I noted that this exponential arrow D is monic is a monomorphism because iota is epimorphism. Since the codomain is the trivial metasimilarities, so iota is a surjection. Okay. Okay, so anyway, I find some exponential arrow in the category L. Then to see that this exponential arrow D is universal in some sense. First of all, recall that any exponential monomorphism induces internal preorder. So that is by the exponentiability of D, we get an internal category, but D is a monomorphism, so this internal category is actually internal preorder. Then important observation is that internal preorder associated to D is isomorphic to the universal metasimilarities. This is straightforward actually, because the universal internal metasimilarities can be described concretely, so I can check if they are equivalent, if they are isomorphic. And then essentially from this, we get that L is a free category with finite limits with an exponential arrow D, which is a monomorphism, and such that the associated internal preorder is internal metasimilarities. Okay. Okay, so then let us look at contextual categories, the main topic of this talk. So contextual categories are introduced by Cartmel to study basic structure of dependent type theory. So anyway. Okay, so as the name suggests, contextual category consists of, first of all, category C, but with more structures. One structure is a tree structure on the set of objects, which I denote. Yeah, so tree structure is a kind of binary relation satisfying certain conditions. And I refer to this binary relation as this triangle. And then for any A and B, such that, let's say maybe A is a parent of B or something like that, then we get an arrow from B to A. This arrow is a kind of projection-like morphism, and it plays a special role in the theory of contextual categories. And it is denoted by this arrow with triangle head. And finally, so this B to A, this PB is like a projection-like morphism, so it should be stable under Pruvac. So the fourth structure ensures that these projections are stable under Pruvac. But one remark is that this is part of a structure, so some specific Pruvac square is chosen. Okay. And the contextual category is required to satisfy some conditions like the root of this tree is a terminal object, and this operator is functorial strictly. And the morphism of contextual categories is functor preserving everything strictly. Then we get the category of contextual categories. Yeah, and so this definition is highly motivated from the theory of dependent type theory, and a typical example is comes from some dependent type theory. So given any dependent type theory, you can always form a category of context and the context morphisms. And so context is a kind of list of variables and types, and we define a relation, prefix relation, which form a tree structure on the set of contexts. So right, so this is a typical example of a contextual category. And in fact, it is the only examples of contextual categories, basically thanks to the Cartman's results on the equivalence of contextual categories and generalized Arabic theories. Any contextual categories can be presented as a syntactic category of dependent type theory.
Sorry, one question. You probably already said it, but by generalized algebraic theory, you mean essentially algebraic or something different?
Yeah, by a generalized algebraic theory, I mean generalized algebraic theory introduced by Cartman.
Okay.
Yeah, right. Okay. Okay, so yeah, anyway, so yeah, this is, so our contextual category is like this. Right, and so at first sight, the theory of contextual categories is not essentially algebraic because of tree structure. But it turns out that a tree structure is, but maybe, you know, a tree structure is equivalent to a chain of sets, which looks like this. This is obtained by splitting the set of objects by the depth of the objects. So A is a set of the objects of depth 1, and A2 is the objects of depth 2, and so on. So a tree is equivalent to a chain of sets. So from this view, the theory of contextual categories become essentially algebraic. And precisely this described like, so it has a kind of chain of sets And so now the set of objects are split into a countable chain. So the families of morphisms become also index of objects of depth n and objects of depth m. Okay. And then I impose a bunch of partial operators and equations to make to construct the essential algebraic theory of contextual categories. So then we know that the category of contextual categories is locally finitely representable. To find a category with finite limits G, which I denote by G, such that this equivalence holds. Okay. Okay, so I try to find a universal exponentiable arrow in G. Okay. So again, I follow the general scheme. So first of all, I construct a free contextual category generated by an object of depth 1. It's fine. And then I freely adjoin a global section of this object sigma. Then we get some another free contextual category. And then my first claim is that this canonical morphism between these free contextual categories determines an exponential morphism in G. And to do this, I again observe slice construction. But in this case, the slice of a contextual category is not the same as the slice of the underlying category. Because we have to take care of the tree structure. So the slice of a contextual category is defined as follows. So an object of depth n in the slice over A is an object of depth n plus 1 in C, which is above A. I mean, this chain of relations hold. And the morphism parts are, and the morphism in the slice are the same as the slice. Just sorry, the morphisms of the slice contextual category is the same as the morphisms of the ordinary slice category. And then the pullback along the terminal projection defines a morphism which I denote A star, which is defined by like this. Namely, given an object of C, then by the tree structure, there is a chain of the projection maps to the terminal object, and the projection maps are stable under pullback, so we get some object pullback along this bottom map. Then the diagonal arrow on A determines the global section in the slice. And this data fits into this commutative square, like an object A corresponding to a morphism from this free contextual category, and the global section delta A corresponds to this bottom map. And because the codomain of the this global section delta A is A star A, which is equivalent to that this square commutes. Okay, so then I claim that this square is pushed out in the contextual category of contextual categories. Again, the proof is straightforward. So given another morphism f from C to D, and again morphism U, which makes this diagonal commutes, this outer square commutes. Then I have to find a unique filler from C over A to D. And this is defined as follows. So given an object of the slice, it looks like a chain of projections over A. Then first I map this chain by F to obtain a chain from F of B to F of A. And now this morphism U corresponds to a global section of F of A. So we have a pullback of F of B along the arrow U. And we just define F prime B to be this pullback. And as this picture suggests, pullback factor always preserves the tree structure. So any pullback factor induces a morphism of contextual categories. So this F prime defined in this way is indeed a morphism of contextual categories. Okay. So now we can so then observe that these three contextual categories are finitely presentable, and the slice construction preserves limits. Then it follows that we can find the exponential arrow D in G, which corresponds to the inclusion. Okay. And so the next I want to prove that this exponential arrow D is a universal one. So to do this, I again compare this exponential arrow with the universal internal contextual category. So because these exponential so given any exponential arrow, we can define a polynomial factor PD like this, where D lowest is the right adjoint of the pullback factor. Then applying the polynomial factor repeatedly to the terminal object, we get a chain of objects in G. It looks like this. And in fact, this is part of an internal contextual category in G. So for instance, PD and so this object PD to 2 of the terminal is a kind of object of objects of depth n depth 2, something like that. So this chain describes the object part of the internal contextual category, and the morphism part is also defined in a natural way. Then we can observe that the internal contextual category associated to the exponential arrow D coincides with the universal internal contextual category. Then it follows that G is the free category with finite limits and with an exponential arrow. Okay, so yeah, so this was which I want to prove. And yeah, so this results can be extended to many other categories of theories. So for instance, the usual slice construction works for example, categories with finite limits, correct categories, regular or coherent categories, and elementary toposes. So in these categories of theories, the ordinary slice categories, the ordinary slice category is a push out. But push out in some higher dimensional sense, of course. So in right. But for some notions of theories, the ordinary slice construction doesn't work. So for instance, categories with finite products are not closed under slice. So, but for such theories, there is an alternative construction called the simple slice. Then it is known that the simple slice is a kind of push out. So it follows that we can find some exponential arrow we can find some exponential arrow from the category of categories of finite products or of Cartesian group categories or Lovia theories. And finally, as a final remark, I should mention closely related work by Fiore and Mahmoud. They constructed the universal exponential object and gave a connection to the theory of clones. Yeah, so they construct. I think why one of their results was the algebraic theory of clones is characterized as a category with finite products and with universal exponential object. Right. Okay. Yeah, and I finish my talk. Yeah. Thank you very much.
Thanks very much, Taichi. If you want to give an applause, how about we try this time to do, on the bottom of your screen, there's reactions. I'm going to try and clap. Does that do anything? Anyway.
Yeah, I can see a clap on your picture.
Okay. Well, thanks very much, Taichi, for the nice talk. And if there are any questions, people feel free to go ahead and ask one.
I have one question, if I can. I'm a little bit surprised or fascinated by the fact that everything you do is very one-dimensional, and the category of contextual categories seems to me naturally a two-category.
But yeah, no. This is because, well, in the definition of contextual categories, this Bruback operator is chosen strictly factorial, and the morphism of contextual categories is chosen strictly preserving functors. So actually, we view the category of contextual categories as just one category. rather than two category.
No. So if you put pseudo functors, then you get a 2-1 category.
Yeah.
But you could really get a genuine 2 category, looking at natural transformations which are not invertible between functors. And I wanted to know, like, this is just a comment maybe, could you say why this 2-dimensional structure plays no role? Because in a way I would expect that that it should play a role.
Well, all right. Maybe. So,
I mean, it's a very vague question, so you can just skip it if you want. I understand that. Well, I understand that. It was just a curiosity.
Yeah, but to my understand, contextual categories are, I think just an algebraic structure rather than a category with structure.
I see.
So that's why I don't know.
Okay, thank you.
So are there any further questions?
If I might ask a question?
Yeah.
Thank you, it was a very interesting talk. I was wondering if maybe you could give a couple of examples on your last slide of what the corresponding universal property of some of these theories were, just to get a bit more intuition for what's going on.
Yeah, I think very roughly. So for instance, for the categories with finite limits, we will find exponential arrow such that the associated internal category has finite limits. I think it's, but I have to be careful maybe. Because for categories with finite limits, we have to deal with at least 2-1 categories. So, yeah, but the idea is basically same as the case of the meter-semi lattices. So, for instance, so for categories with finite limits, we will find an exponential morphism whose associated internal category will be finitely complete, and for locally Cartesian closed categories, we will get exponential arrow such that the corresponding internal category is locally Cartesian closed, and so on.
All right, thank you.
So one question I have, so this syntactic proof that you mentioned, is it related to this semantic counterpart, or those go through different ideas?
Well, yeah, they share some ideas, but how to say it? Yeah, of course. Well, the target exponential arrow. So in both proofs, these exponential arrows are constructed in the same way, but for the proof of exponentiability, But I think it's in the syntactic proof. I think I am doing some construction corresponding to the slice construction. I guess.
Okay.
But yeah, but I didn't make a precise connection.
Okay, thank you.
Okay. Well, if there are no further questions, let's thank Taichi again as you see fit. And yeah, so thanks for the talk. And next week we have a talk by Christian Espindola. So look forward to seeing you then, so we can stop recording. And that's it for today. So thanks and bye.